6 months ago, our PS3 was running like this. Today, we're able to emulate the PlayStation 3 60% faster while drawing 25% less power. So, how did we do it? It all started with this document, the ARM Architecture Reference Manual. It's over 17,000 pages long. Now, since this document only exists digitally, I stacked some books as an example to show you what 17,000 pages would look like in real life. I scoured every digital page of this document to bring PlayStation 3 emulation to a new class of devices. Last Christmas, I ordered this handheld device, the Ein Odin 2. It's basically an Android smartphone, but with controls bolted on. But rather than using it as an Android device, I actually bought it so that I could install Linux on it and optimize RPCS3 for ARM. Seriously, it's much cheaper than an ARM laptop with similar hardware. Anyways, the first thing I noticed when I received and booted the device in January is that we're spending half of our CPU time in this little 4-line function, busy wait. Alright, so the reason this function exists is to improve performance in multi-threaded code. Imagine a piece of code that's checking if another thread changed a variable, over and over again in a loop. That will ensure that the monitoring thread can see the change as fast as possible, but it's going to produce extra heat, burn more power, and put additional pressure on resources shared between cores, like cache and memory. In the past, I actually helped our former lead developer Neko Tekina in debugging an issue, and what we found is that when we added a busy wait to a particular place in the code, we managed to triple our performance. Under some pretty specific circumstances, but still. Now, to understand why busy wait was so slow on my ARM device, we need to explain how it works on an x86. First, we read the hardware timer and add 3000 to it to get our target wait time. Then, we call the hardware timer in a loop, waiting until the hardware timer exceeds the initial value plus 3000. Additionally, we call the pause instruction in the loop too, which throttles the hardware even further, offering even greater power savings. Inside busywait, we added this arbitrary value of 3000 to the timeout, which works out to about a 1 microsecond wait on most x86 devices. The speed of the hardware timer on x86 devices depends on the specific device, but since the hardware timer is typically running somewhere between 2 to 4 GHz, this works out to about a 1 microsecond wait. Again, remember that this isn't intended as a precise wait or anything, but just a way to save some power. It would be trivial for us to do some math and wait for a precise period, but that would require extra memory reads and multiplications, which would defeat the purpose of our simple, hardware-friendly busywait function. When porting the code to ARM, we did the straightforward thing. We replaced reading the hardware timer on x86 with reading the hardware timer on ARM. We also mapped the pause instruction on x86 to the yield instruction on ARM. But what speed does the hardware timer run at on ARM? At least on my device, it's running at 19 MHz. That's 150 times slower than what we expect. Meaning that instead of waiting for 1 microsecond, we're actually waiting for 150 microseconds each time we call busy wait. The solution to this stupid problem is to simply just scale the amount of time spent waiting by the frequency of the timer. Yeah, we have to do the extra math, but it's much better than waiting 150 microseconds each time we call the function. After consulting Google search, we've learned that ARM hardware timers typically run between 10 MHz and 1 GHz, so there's no one value that's good enough for all ARM hardware. Just fixing this bug alone provides a 25% boost to performance on average, on top of reducing power draw by 10%. Another user reported going from 5 to 10 frames per second, all the way up to a locked 30 frames per second on his ARM-based MacBook in Skylanders. Fixing this tiny issue alone is already enough to let the hardware stretch its legs. The fact that such a simple fix was already having such a large impact filled me with the determination and confidence to tackle the rest of the low-hanging fruit. Yum. Moving back to the present, after all our optimizations, which we will be exhaustively covering in this video, the CPU side of RPCS3 is so fast that many games like Demon's Souls are now bottlenecked by the host GPU. We went from being CPU limited in the majority of our games to GPU limited in many of our games. In some other games, the uplift to CPU performance is even more obvious. When looking at Ninja Gaiden 3, there's a similar uplift in performance compared to Demon's Souls across many scenes. Not bad. But when we look at actual gameplay, you'll probably notice that the game is running in slow motion with the older code. The game logic can't run at full speed on the older builds. That's great and all, but the busy wait bug existed from the very first version of RPCS3 on ARM, back in January of 2022. It took 4 years to resolve this bug, despite how simple the fix actually is. Why did it take so long to fix? Well, Neko Tekina, our former lead developer, ported the emulator to ARM, but left the project before finishing work on the recompilers, which are needed to run almost any game at full speed. Our lead graphics developer KD11 stepped up, purchased ARM-based Apple hardware, and got the recompilers functioning. With everything functionally ported, KD11 moved back onto working with the graphics backends. While the emulator was functionally ported to ARM, there were a lot of niggling issues left over, with no one actively working on them. Fortunately for you guys, that means you get a dense, interesting video where I talk about a whole ton of niche assembly code. You're all elite hacksaws, right? Remember when people used to call themselves that? Anyways, this handheld is the Iron Odin 2, the ARM device that I picked up. It's a Chinese Android gaming handheld, and it's several years old now. Unsurprisingly, it's pretty good at playing Android games. You can also run all kinds of emulators on it. It's even capable of playing PC games from Steam, like Silksong, but I didn't order it to play around with it. Actually, by the time I ordered it, the much faster Odin 3 was already released, but I still opted to pick up the Odin 2 because the chip in the Odin 3 has cores that don't support SVE instructions, which was something that I wanted to support in the emulator. Also, installing Linux was supported for the Odin 2. At the time of making this video, Linux installs are now possible on the Odin 3, but that wasn't a thing last December. There are two PlayStation 3 emulators for Android, both based off of upstream RPCS3. There's APS3E, which was the first to release. When APS3E was initially released, it was closed source, which is a violation of the open source license that RPCS3 is released under. The current versions of APS3E are open source correctly, so kudos to the developer for turning around on that issue. RPCSX is the second PlayStation 3 emulator for Android. RPCSX is headed by DH, who you might also know as the founder of RPCS3. Despite the presence of these Android PlayStation 3 emulators, I chose to install Linux on my Odin 2, because I work on the upstream version of RPCS3, which works on Windows, Linux, and Mac devices. Some of you are probably wondering, do the optimizations I'm talking about in this video apply to these Android versions of RPCS3? Well, at the time of recording this video, the answer is no. But if these Android versions of RPCS3 were to rebase themselves onto the upstream code, then yeah, they could. With all that background out of the way, let's move back to busywait, because there's one more issue lying in this function. If you recall, we used the ARM yield instruction in place of the x86 pause instruction. Let's review the definition of yield from the ARM manual. Yield is a hint instruction. Software with a multi-threading capability can use a yield instruction to indicate to the hardware that it is performing a task, for example, a spin lock that could be swapped out to improve overall system performance. Oh, awesome. That sounds perfect for our use case. Remember, on x86, the Intel manual refers to pause as a spin loop hint. But if you scroll down to another section of the ARM manual, you'll find this. In a symmetric multi-threading design, a thread can use the yield instruction to give a hint to the processor that it is running on to indicate that whatever the thread is currently doing is of low importance. Here's the problem. Yield only yields the current thread if the hardware has SMT, but 99% of consumer ARM machines don't use SMT, they use traditional SMP cores. On an SMP system, the manual says it can lower the priority of the snoop bus, but since we aren't reading any memory in our busywait loop, that doesn't change anything either. ARM actually published an entire blog post explaining how to port a busywait-like function that uses x86's pause over to ARM. They call out yield, but explicitly mention that it is treated as a complete NOP on systems without SMT. This doesn't technically contradict the 17,000-page reference manual, but it reveals that yield does absolutely nothing on almost every modern ARM phone, tablet, and laptop. Instead of using yield, we now use the instruction synchronization barrier instruction, also known as ISB. The same blog also mentions that ISB isn't ideal for replacing pause, as it causes the machine to restart instruction fetch, burning a little more power, rather than properly stalling both instruction fetch and execution. Of course though, saving power isn't the intended use case of ISB. However, despite all the caveats, use of ISB does save a little more power in this loop over yield. By the way, you can just look for pull requests that mention yield or ISB on GitHub, and you can find code from all sorts of multi-trillion-dollar corporations who ran into the exact same issue we did here. The description of yield in the manual could probably be adjusted to avoid this issue. Here's a little illustration of how ISB helps us throttle our CPU usage.
True, and yeah, that's pretty true. That's true, and yeah, that's true. That's true. That's true. That's pretty true. That's pretty true. I mean, true, and yeah, that's pretty true. That's true, and
with ISB, the CPU is able to save power by only checking the condition once per several nanoseconds, rather than multiple times per nanosecond. These tiny changes have already improved RPCS3 a lot, but from the start, what I had my eyes on was the recompiler. The SBU recompiler is typically the heaviest part of emulating the PlayStation 3 on x86 machines, despite the x86 backend having been relentlessly optimized. I dove straight into the assembly that LLVM produced, and this is what I saw. Just as a recap, RPCS3 uses the LLVM project to translate PlayStation 3 game code to x86 or ARM. We take PlayStation 3 assembly, Translate that to LLVM IR, then LLVM takes that and outputs native code for your machine. It's not dissimilar to how games like Unleash Recompiled work, only they're translating to C rather than LLVM IR. Unleash Recompiled even requires use of the LLVM-based Clang compiler to recompile the C code it produces, so you can think of it as almost the same approach, really. The advantage of using LLVM over directly writing assembly ourselves is that we can take advantage of all the optimizations that LLVM already knows how to do. Of course, LLVM isn't perfect at optimizing and has done a pretty bad job at optimizing some instructions. But before we cover how everything was fixed, let's review the things that ARM and LLVM were able to do better than the x86 backend without any intervention. The SBU instruction absdb takes the absolute difference between two numbers, that is to say, it finds how far apart two numbers are. So, for instance, the absolute difference between 3 and 7 is 4. x86 has a number of instructions that calculate absolute difference, but they all sum the values horizontally too, so we need this 3 instruction sequence to calculate the absolute difference, which works out to this expression. On ARM, we just have an instruction that calculates absolute difference the same way as the PlayStation 3. Nice. For count B, the situation is similar. We have an instruction that just matches PlayStation 3 behavior. This instruction counts the number of bits set in each byte, which is pretty expensive if you don't have an instruction to accelerate this. Anyways, x86 can also do this in a single instruction, if you have AVX512. Else we need this awful sequence to count bits properly. Similarly with CLZ, we have a single instruction solution for ARM, as well as x86 CPUs with AVX512. This instruction counts the number of zeros in each byte until it finds a set bit. And again, the non-AVX512 x86 path requires an extreme number of instructions. CLGT is a simple instruction, performs an unsigned comparison. Of course we need 4 instructions on x86 to emulate it. Why wouldn't we? With AVX512 we need 2 instructions, as AVX512 adds an unsigned comparison instruction. But since AVX512 compares directly into the mask registers, we still need another instruction to move the result into the vector registers. ARM, of course, just has an unsigned comparison instruction, so we only need 1 instruction to emulate CLGT. Finally, we have SHUFB. For ARM, BSL is a single instruction solution here. Again on x86, we need 3 bitwise instructions to emulate SHUFB. If we have AVX512, we can use VP turnlog instead, which can do any permutation of 3 bitwise operations on 3 sources at once. It's like a Swiss Army knife of bitwise instructions. So, in some cases ARM can have more optimal codegen than x86, but in most cases that gap is closed if our x86 machine supports AVX512. Now, this is all nice, but that's just 5 instructions where ARM could beat x86. There were dozens of instructions where the ARM codegen was worse than the x86 output. Fortunately, that's all fixed now, and yeah, we're gonna review how every single one of them was fixed. For the first instruction, SHUFB, that bad codegen was our fault. See, when importing the LLVM recompilers to ARM, we just emulated the x86 pSHUFB instruction instead of properly rewriting the emulation to use ARM shuffle instructions. In LLVM IR, there exist generic shuffle operations that will compile down to whatever shuffle instruction is ideal on the host machine. It's really good at this actually. But the generic shuffles only take constant indices for the shuffle operations. This is because variable shuffles, like SHUFB on the PlayStation 3, pSHUFB on x86, and TBL on ARM, all have differing behaviors, so there's not a reasonable way to create a generic operation here. And so the fastest way to get the recompilers working was to just emulate x86 pSHUFB. That way we didn't need to rewrite the emulation of any of our PlayStation 3 instructions. Of course, this has provided us with the lowest hanging of the lowest hanging fruit, and boy is that fruit ripe. By rewriting emulation of SHUFB to properly use the ARM shuffles, we cut the number of needed instructions from 10 to 5. Yeah, it's still a lot larger than the 1 instruction solutions we were discussing for the other instructions, but SHUFB is simultaneously one of the most complex PlayStation 3 instructions, on top of being one of the most common. So optimizing it as much as possible is paramount. Let's break down how the unoptimized version works first. I'm gonna do it in an order slightly different to how it's laid out here, but bear with me. First, we need to XOR the bottom 4 bits of the indices, since SHUFB uses a big endian byte ordering, while TBL on ARM uses a little endian byte ordering. Essentially, both these instructions read shuffle indices in reverse order from each other. Next, we need to AND our result with hex 8F to mask out everything but those bottom 4 bits, as well as the most significant bit. Then, we need to feed these indices into TBL twice. Since TBL will zero the result if any bit outside of the bottom 4 bits are set, we had to mask off bits 4 to 6 while leaving bits 0 to 3 and bit 7 untouched. Thus when bit 7, the most significant bit is set, we will place 0 in the result, matching SHUFB. Next, the sequence of 3 instructions will combine the results of the 2 TBL instructions based off of the 4th bit. We shift the 4th bit into the most significant slot, compare to generate a mask based on whether or not that bit was set, then select between our 2 TBL results from earlier based on the mask. This is needed because the PlayStation 3 SHUFB shuffles from 2 table sources, while TBL only takes 1. At this point, we've correctly emulated the shuffle part of SHUFB, but SHUFB also has 3 different constants that can be produced when the most significant bit is set. When the most significant bit is set alone, we produce 0. When the most 2 significant bits are set, we produce hex FF. And when the most 3 significant bits are set, we produce hex 80. 3 different special cases is a lot. To produce them efficiently, we need to use TBL again. We first shift the 3 most significant bits such that they're located in the lowest 3 bits. Then, we use TBL along with this constant to successfully generate our constants in each slot. Finally, we bitwise OR our generated constants into the shuffled data from earlier. Since we kept the most significant bit in our shuffle indices, we conveniently have 0 in all of our slots where constants are. 10 ARM instructions later, we've emulated 1 PlayStation 3 instruction. It's rough. Fortunately, there's some very low-hanging fruit here. The instruction TBX is like TBL, but when out-of-range indices are used, it instead takes the value from the destination register instead of filling it with zeros. This allows us to skip the final OR instruction. Additionally, TBL and TBX can actually take multiple registers as shuffle inputs. Between 1 to 4 registers may be used in this manner. This means that we can simply use TBX with 2 input registers, replacing this entire 5 instruction sequence. That brings us down to just 5 instructions, half as many as we needed initially. Pretty awesome! It could actually be just 4 instructions. There's an instruction BCAX, which performs both an AND as well as an XOR operation at the same time. This instruction is part of the SHA-3 instruction set, intended for accelerating cryptography. But unlike the other cryptography extensions, SHA-3 is full of bitwise instructions that are also useful for general purpose code. That was a lot to take in, so let's take a break by looking at this family of skunks. Anyways, LLVM is capable of combining these operations into a single BCAX. It seems like LLVM can only pattern match BCAX when the inputs aren't constants. Of course, we kind of need them to be constants. I opened an issue for this on the LLVM GitHub, so hopefully this is something they'll address. Still, even if they did, 4 instructions for one of the most common PlayStation 3 instructions isn't exactly ideal. Thankfully, all of the other optimizations we've written over RPCS3's existence for SHUFB will still apply here. For instance, if SHUFB is used within a loop, we can calculate all of the special cases outside of the loop, reducing our usage of SHUFB within the loop to just a single TBX2 instruction, which is pretty awesome. 4 instructions to set up our SHUFB emulation, and just 1 instruction to emulate it 1,000 times in a loop. When I went to test our optimized SHUFB, I was able to see an 8% performance uplift, a testament to how important this instruction is to the PlayStation 3. Pretty awesome for optimizing our first instruction on ARM. Except half the games now refuse to boot. Alright, since using TBX or TBL with 2 inputs vectors requires both input vectors to be adjacent in the registers, this places a lot of constraints on the register allocator. And with how LLVM is configured in RPCS3, it just seems to give up at a certain point and crash with this message. So I was left with 2 choices: give up on the optimization, or just enable it for games where it doesn't break. But that really sucks as we're talking about an 8% uplift here. I was really bummed out. After that fix to busy wait and now the SHUFB optimization, I felt like I had real momentum, but now I didn't know what to do. It took me some time, but after an obscene amount of testing and debugging, I settled on the world's stupidest solution. Just catch the crash when LLVM fails to compile a block with 2 source TBX or TBL. Then retry it with a single source TBX and TBL. It's an absolutely awful solution, but hey, when 10,000 recompiled blocks compile successfully with the 2 source versions, and only 3 blocks need the fallback method, we can keep our 8% speedup, and keep all of our compatibility. With all of that solved, I've moved on to porting some more optimizations over to ARM. I've been making YouTube videos on RPCS3 optimizations for a while now, and since the optimizations I've covered thus far focused on x86 machines, many commenters expressed interest in coverage of simpler instruction sets. Here's the secret though, ARM is every bit as complex as x86. It's an absolute mess actually. You know, when the first M1 MacBooks came out, there was this anecdote from one of the designers of the original ARM system that kept appearing in every YouTube review, where they didn't hook up the power supply to the ARM chip, and yet it was still running off parasitic power from the rest of the system. Look, I'm a YouTuber too. I understand. It's a nice little anecdote, and it adds to the storytelling of a review video. But the ARM chips of the 80s don't have anything to do with the ARM chips of today. I mean, modern ARM chips are massive machines with a massive instruction set. The manual alone is 17,000 pages! I mean, just look at this. These 3 instructions have separate encodings, but have identical behavior on a device with ARM's latest consumer-focused cores. It's a mess, man. Look, a lot of people have said something along the lines of, wow, VPDPBUSD, what a complex instruction! Nice optimization, but what will you do on simpler instruction sets like ARM? But the ARM instruction US dot behaves identically to VPDPBUSD. Having simpler mnemonics doesn't make it a simpler instruction set. Maybe I'm making a mountain out of a molehill here, but the point I'm trying to make is that modern ARM has way more in common with modern x86 than ARM machines from the 80s. There's a silver lining to this though. This means that a number of optimizations we can make are going to just be straightforward ports of x86 optimizations to ARM. I can't count the number of times I read on Reddit or YouTube that RPCS3 needs a complete rewrite, or a brand new emulator needs to be born to properly take advantage of ARM hardware. And it's like, no dude, we just gotta put the square in the square hole. It's pretty straightforward, really. I covered SUMB in more detail in this earlier video, but to make it short, this instruction sums 2 vectors horizontally like this, then packs the result, like this. x86 and ARM both have dot product instructions which first multiply bytes vertically, then sum horizontally. So by using these dot product instructions with a multiplicand of 1, we can sum in the same way that SUMB does, and then pack the result as needed. Adding this optimization to ARM was as simple as dropping the udot instruction in where we were previously using VPDPBUSD. Anyways, one more place where dot product instructions are applicable for RPCS3 is in emulating the gather bit family of instructions. On x86, we haven't elected to use the dot product instructions, as x86 has access to the move masked family of instructions, which can emulate the bit gather operations in a fairly idiomatic way. We also have an insanely optimized implementation which uses the Galois field instructions if your machine supports them. Let's take you through the dot product based optimization. All GBB does, essentially, is take the least significant bit from each byte, and pack them, like so, zeroing out the rest of the register. This time, when using the dot product instructions, we're going to make use of another cute trick. Instead of multiplying by 1, we instead multiply by powers of 2. Essentially, by using a different power of 2 for each lane, and by masking off everything but the least significant bit, we can use the dot product instruction to essentially gather bits for us. Since each result of our dot product will only contain 4 bits, we need to shuffle our results into the correct lane, then execute this add pairwise instruction to horizontally sum our results into the correct location. Pretty slick. But most of the time the gather bit instructions are used. They're used following a comparison instruction. Comparison instructions fill a result with -1 or 0. -1 and 2's complement means that all the bits in the number are set. Here's the trick though, by multiplying with a negative power of 2, we can skip isolating the least significant bit, saving another instruction. The dot product instructions on both x86 and ARM were added with the intent of accelerating AI, but they're useful outside of that domain as well. ARM actually goes further than x86 in this regard and has even more powerful AI instructions on modern ARM machines. The UMMLA and SMMLA instructions from the i8MM extension help us economize even further on instruction count. These instructions split each half of both input vectors into 8 bytes. The first half of the first vector is multiplied against both halves of the second vector, horizontally summing each result, and same with the second half of the first vector, producing 4 results. We can apply the same sign trick when the input is a result of a comparison. This means that we only need 2 instructions to emulate the common case of GBH and GBB, which produce 8 bits and 16 bits as a result respectively. Since GB produces just 4 bits as a result, the existing dot product optimization from earlier already achieved a 2 instruction solution. Slick. Let's move on to some more straightforward uses of multiplication. The SPU integer multiplication instructions are all 16 bits times 16 bits, but they produce 32-bit results. To emulate these instructions, we mask off an appropriate number of bits, then just throw 32-bit multiplies of x86 or ARM at them. We also have some pattern matching that follows this 32-bit times 32-bit multiplication pattern from the SPU manuals, and simply emulate that with a single instruction. Sweet. But ARM actually also has widening multiply instructions. Instructions that do 16 bits times 16 bits and produce a 32-bit result. Only problem is, they expect the inputs to be packed in a form that's quite different from how the SPUs expect them. That being said, we can still save some instructions by using these widening multiplies. Looking at the most straightforward of the SPU multiplies, we have MPY. It's a sign multiplication. Instead of simply masking off the upper bits, we need to first shift the bottom 16 bits left 16 bits, then shift those back right, to sign extend those numbers to 32 bits, such that we can properly perform sign multiplication. When using the widening multiplies, it looks like this. We can use the XTN instructions to take the low order 16 bits from each 32-bit lane, and pack them in the low 64 bits of the vector. We do this again for the other input, and then we can use the widening multiply, SMLAL, which will take the packed 16-bit values in each 64-bit input, and place the 32-bit results in the expected 128-bit vector. That brings us down from 5 instructions for MPY, down to just 3. There's a wide variety of SPU multiply instructions. Here's what we were able to save with similar optimizations for the other SPU multiply instructions. The SVE2 versions of widening multiplies are even more useful for our PS3, but there's a lot of caveats to the SVE instruction set extensions that I need to address before we can talk about them, so let's bury that thought in the sand for now. Let's first cover the rest of the Neon optimizations that all ARM users can benefit from. Alright, FCGT is one of those instructions where I compared the ARM LLVM output to x86 earlier. Suffice to say, LLVM completely dropped the ball when it came to optimizing this code. I'm not even going to attempt to explain what it's doing. I tried massaging the code all over to see if I can get rid of this bug, but nothing seemed to work right. In the end, the only thing that worked was adding inline assembly of the instruction I expected to be there, BSL. FCGT is a difficult instruction to emulate. It's just a floating point comparison, but on the PlayStation 3's SPUs, NAND and Infinity don't exist, so we need to work around that. To properly emulate the instruction, we need a comparison to see if A is bigger than B, then perform a second comparison to see if B is smaller than A. Then, based on whether or not both inputs were negative, we select between the two results. The BSL instruction is what does the select. All this nonsense was replaced with BSL. 15 instructions down to just 7. It's unfortunate because using inline assembly to address this issue inhibits further optimizations from LLVM. I opened an issue for upstream LLVM, such that we can drop this workaround when it's addressed. The FSM family of instructions exhibit another complete failure to optimize by LLVM. This is despite the same code optimizing just fine on x86, and all the same instructions existing basically one-to-one on ARM. Let's first explain what the x86 code is doing here. FSM is basically the reverse operation of the gather bits family of instructions. It takes the compacted bits from a gather bits operation and expands them into byte, 16-bit, or 32-bit elements of all zeros or all ones. So on x86 we broadcast that packed value to all the lanes, and that value with a constant to mask off the appropriate bit that will expand into all ones or all zeros, then compare with that same value we ANDed with. Only 3 instructions are needed. The ARM code, on the other hand, is absolutely insane. It starts by using this SBFX instruction, sign bit field extract. Essentially, it's grabbing one bit at a time and extending it to all ones or all zeros. Then it grabs those expanded bits and inserts them into a vector. But then it does it again, and again, and again. It entirely scalarized this vector operation. It's awful. Anyways, I opened an issue on LLVM's GitHub this time too. The workaround is just to write the LLVM IR to be more idiomatic, basically matching what the x86 code did. The funny thing? This way we end up with a solution that's only 2 instructions, faster than the x86 way. See, ARM has the instruction CMTST, which is basically a combined AND plus compare instruction. It's pretty sweet. Next, we need to fight LLVM again to optimize all these instructions. The SHL instructions are shift left instructions. The ROT-M instructions are shift right instructions. They actually stand for rotate and mask, but a rotate that masks in zeros is basically just a shift. These instructions first mask off a certain number of bits depending on the size of the elements that the instruction operates on. For instance, the shift left word instruction masks off everything but the bottom 6 bits. In this case, the bottom 5 bits indicate how much to shift. If the 6th bit is set, then we fill the result with 0. On x86, shifting works the same way, except it doesn't mask off the upper bits, so if any of them are set, all zeros will be shifted in. So then, to emulate the PlayStation 3 behavior correctly, we just need one AND instruction to mask off everything but the bottom 6 bits, and then execute one shift instruction. So just 2 instructions are needed. The ARM equivalent shift instructions work the same way as x86, with one exception. Instead of having a shift left instruction and a shift right instruction, the USHL instruction shifts left if the value is positive, and shifts right if the value is negative. Alright, but that doesn't matter for emulation of PS3 SHL. But then why is the same LLVM code compiling down to 4 instructions for ARM? Okay, so the LLVM IR for shifts leaves part of the implementation undefined. When you expect to shift in zeros, we actually shift in something known as poison values. So we need this code to replace the potential poison values with zeros. We expect the optimizers to handle this, and just realize, oh hey, the native shift instructions on this machine will shift in zeros. But for whatever reason, that's not working on ARM. Anyways, once again, I've opened an issue with upstream LLVM, and implemented a workaround by using the intrinsic for USHL in the meantime. That saves 2 instructions for each shift instruction, mostly matching x86. The ROT-M instructions still require 1 instruction over x86, as USHL needs the shift count to be negated to rotate right. With that, we've covered the most catastrophic codegen issues. But now, it's time for something completely different. So far, we've been optimizing the obvious things, the low-hanging fruit. They were so overripe that they started to ferment. But I wanted something more interesting. The kind of interesting that comes from staring at hardware manuals until you're delirious. And man, ARM hardware like the Snapdragon 8 Gen 2 on this Odin 2 leads to all sorts of interesting. Actually, it's technically a Dragonwing QC8550. Which is basically just a Snapdragon 8 Gen 2 without the wireless functionality expected of a smartphone, but the marketing material for the Odin 2 still calls it a Snapdragon 8 Gen 2, and I'll also be referring to it as such for the rest of this video. Anyways, the Snapdragon 8 Gen 2 is pretty unique as it features 4 different core types. The Cortex-X3 is the biggest and fastest core, and offers high performance at the expense of die area and power consumption. There are 2 Cortex-A715s, which offer a reasonable balance of performance, power, and size. There are 2 more A710 cores which are essentially the previous generation of A715s. Why are they included? Well, the X3 and the A715s drop support for 32-bit ARM instructions, so Qualcomm included the A710 so that 32-bit programs could still run for one more generation with reasonable performance. Finally, there are 3 small cores, the Cortex A510s. These cores are quite slow, but sip power and barely take up any die space. Unfortunately, many of the concessions made make them quite inadequate for PlayStation 3 emulation. For instance, these 2 Cortex A510s share a single 128-bit vector unit, so when we're emulating SIMD heavy PlayStation 3 code, even if every PlayStation 3 instruction was emulated with one host ARM instruction, the A510s could still end up being significantly slower than the original PlayStation 3. The third A510 actually doesn't share a vector unit, but it has exclusive access to a 64-bit vector unit, so 128-bit instructions execute at half the speed. So, really, if you count the clustered A510s and the unclustered A510s as different core types, you're looking at 5 different cores in a machine with 8 cores total. It's a little ridiculous. You might then consider me absolutely insane for attempting to micro-optimize for this hardware, but let me just explain. The A715 and A710 share almost the same behaviors as they share a lineage. The current lineage of mid-cores was sort of crystallized with the A78, then all these mid-cores up to today have a lot of shared behavior. There's one thing that these cores do, which is unusual not just for all other ARM cores, but any other CPU I've ever seen. They can do more vectorized loads than they can do actual vectorized operations per clock. See, if we look at this random Intel CPU, we can do 2 256-bit loads per clock and 3 256-bit vector operations per clock. A slightly newer Intel CPU can do 3 256-bit loads per clock and 3 256-bit vector operations per clock. If we look at the latest AMD core, we can do 2 512-bit loads per clock and 4 512-bit vector operations per clock. Moving on to ARM CPUs, the Cortex-X3, the big core of the Snapdragon 8 Gen 2, is similarly capable of 328-bit loads per clock and 428-bit vector operations per clock. The point I'm trying to make here is that you typically expect cores to be capable of more vector operations than loads, or at least an equal number of vector operations to loads. But the mid cores, all of them are capable of 328-bit loads per clock, but only 2 vector operations per clock. Considering these cores have been so min-maxed in area otherwise, the lopsided load performance is surprising to me. Even if we consider the performance of workloads that stream from memory and need the bare minimum of vector operations, like for instance, with a comparison function, we still need a 1-to-1 ratio of vector operations to loads. How could this capability ever be useful? Well, let's actually illustrate this so that we can understand. When comparing, one way of writing it might be to load one value from each source stream, XOR the 2 values, then OR the result into an accumulator. Then, we repeat that process over and over until all the data is consumed and accumulated. That way, when we check the accumulator at the end, anytime the data wasn't equivalent, we would have accumulated a set bit in the accumulator. This is thanks to a neat property of XOR. Anytime we XOR the same value into itself, we get a result of 0. So, naturally, if we wanted to try and speed up comparison operations on these cores, the first thought is to look at ARM's 3-input bitwise instructions. If each operation could consume an input from each source and accumulate directly, we could save on a lot of instructions and actually utilize all 3 load ports of our ARM mid-cores. BSL, BIT, and BIF don't have any XOR operation, so they're not useful here. EOR3 is just 3 XOR operations chained together, and BCAX is also lacking what we need. So, maybe we can look towards the cryptography instructions. These are also 3-input instructions configured to be useful for just a single algorithm. And yeah, none of these are even close to useful for us. So, fine. What are the remaining instructions we have? Well, we've got instructions which take the absolute difference between 2 values and accumulate that. We've got instructions which multiply 2 integers and accumulate that. We've got instructions that multiply 2 floats and accumulate that. And finally we have the dot product instructions that we use to emulate SUMB and GBB. None of these are obviously useful for accelerating something like a comparison, but I simply refuse to believe that there is no use for the 3 load ports of the most common ARM cores out there. So I just thought about it every day until my third eye opened or some shit because I realized we can use multiply accumulate instructions to accelerate comparisons. Hear me out. When we execute a comparison instruction, what do we get? When a comparison is true, we get a result of all ones, which can also be interpreted as -1. When a comparison isn't true, we get a result of 0, which can be interpreted as 0. Okay. Suppose we tried to multiply two comparison results together, and then tried to accumulate them. What would happen? Well, in each lane where both results were true, we would multiply -1 by -1, adding 1 to the result. If either or both lanes were false, we would multiply by 0, adding 0 to the result. Then, we could just count the number of times 1 was added to the result. We know how long the piece of data that we're comparing is beforehand, so we know exactly what the number of 1s in the result should be. This method allows us to achieve a ratio of 0.75 math operations per load operation, speeding up the comparison by 22% on our ARM mid-cores. Oddly enough, it's also a sizable speed up for the larger X3 core. In theory, the X3 should have been able to max out load bandwidth with the basic comparison code, but it also clearly benefits from the reduction in instructions executed. When it comes to the small A510 cores, there's only about a 16% speedup. Still, the optimization targeted the mid-cores, so as long as the new code didn't slow down the little cores, I consider that a win. As far as I know, this is a novel optimization. It should be broadly applicable too, as almost every Android device comes with a large array of these mid-cores, all of which feature the same imbalanced layout of 328-bit load ports and 228-bit arithmetic ports. Even the Switch 2, for instance, has 8 A78 cores. In RPCS3, I've hooked this up to two parts of the code where comparisons of a fixed length are used. Both should benefit the performance of SBU code. But in one of those places, where we're verifying that the SBU code hasn't changed, we don't actually use a comparison if the code size is big enough. We use a checksum. Just like with comparisons, a checksum ends up using the same ratio of load to arithmetic operations, a 1-to-1 ratio. Of course, the checksum only needs to read half the data that the comparison does, so even with a suboptimal ratio, the checksum is still faster than the comparison. So, how can we speed up a checksum? One idea is to use an XOR sum instead. After all, the EOR3 instruction exists. It XORs 3 inputs together. Perfect! Only, I tried this before, on x86 where AVX512 VP turn log exists. It works quite well, except it caused Grand Theft Auto 5 to crash. Crap.
Oh shit, not good.
So, what can we do if XOR sum isn't an option? Are any of the multiply add instructions appropriate? I don't really think so, since if any of the data is zeroed, it would zero the other result. I think it's going to impact the quality of our checksum way too much. The floating point multiply add instructions are similarly useless, but the cryptography instructions might actually be useful. However, I was dissuaded from trying because on the X3 cores, the crypto instructions only have a throughput of 1 per cycle. Even if we can consume double the data per instruction, we would need to mix add instructions together with crypto instructions, which, strictly speaking, isn't a blocker. But really, I didn't even try playing around with the crypto instructions because the final category of 3-input ARM instructions proved useful: absolute difference and accumulate. This way we consume 2 loads, calculate the absolute difference, then accumulate them with just 1 instruction. The large X3 core is capable of 2 absolute difference accumulates per clock, and 4 adds per clock, while the mid-cores are capable of 1 absolute difference accumulate per clock, and 1 add per clock. So by executing 1 add per every absolute difference accumulated instruction, we can keep all the arithmetic ports filled on every core. Did it work? Absolutely. This time the cores are executing at a ratio of 0.666,
Repeating, of course.
arithmetic instructions per load instruction. In my testing, this sped up the mid-size cores by 38% and the larger cores by 21%. That's awesome. Finally, there was one part of the code that was bothering me for quite some time. The checksumming code, up until this point, was totally unrolled. Rolling it up into a loop when it's large enough ends up being an optimization, as it takes up less space in the code cache. Rolling up the loops is a benefit to both x86 and ARM machines, granting around a 2% increase to performance. On ARM, all 3 of these optimizations combined lead to about a 5% performance uplift. And if you thought that was awesome, look at this. In Stone Talon Mountains, over at Sunrock Retreat, you can wave at the guards and they're forced to wave back at you, giving you freedom to harass all the townsfolk. This is a normal feature of the city guards. They're intended to respond to various emotes, and it's weird that they respond to emotes of the opposite faction. But that's just supposed to be a feature of the city guards. See, with the guards in the crossroads, they just run me down if I wave at them. So, anyways, if they ever release a version of WoW where the level cap is set to 25 again, you can make use of this knowledge. I've been sitting on this footage for 3 years now. Sorry, let's get back to emulation. Just like with x86, ARM machines have a lot of instruction set extensions. New instructions introduced to solve problems that didn't exist when 64-bit ARM was originally introduced. Just like with x86, most of these new instructions are vector instructions. Since RPCS3 is so vector heavy, this means that newer CPUs tend to solve more of our problems. That's why AVX512 tends to be so useful for RPCS3. The fortunate thing with ARM is that Neon, the baseline vector instruction for ARM, is much more well-rounded than AVX2 is on x86. SVE is ARM's equivalent to AVX512, in a sense. SVE stands for Scalable Vector Extension. Just like with AVX512, SVE changes how comparison instructions work. Typically, with AVX2 and Neon, when comparing, we fill registers with 1s and 0s, like we've covered earlier for a few tricks. With SVE and AVX512, comparison instructions now compare directly into predicate and mask registers respectively. These registers are typically used as an extra operand in instructions. When mask or predicate registers are used as part of an instruction, each bit in the register will match up to an element in the instruction. That bit will indicate whether we keep the result for this operation, or whether we just zero the result. For instance, when used like this, we can use SVE or AVX512 to skip one AND instruction in the sequence. Most AVX512 instructions also support a mode where the mask register either overwrites or preserves the content of the destination register, not unlike the ARM TBX instruction. Anyways, since the predicate and mask registers exist now, the old comparison instructions that compare directly into vector registers don't exist in SVE and AVX512. Since we're emulating the PlayStation 3, which uses the compare into register method, that means that even when we have SVE or AVX512, we still need to interleave them with Neon and AVX2 instructions. Now, interleaving AVX512 with AVX2 is easy. All AVX512 instructions can be encoded to work on 128-bit, 256-bit, or 512-bit vectors. SVE takes this even further. SVE vectors can be 128-bit, 256-bit, 512-bit, 1024-bit, or 2048 bits. Except, while the length of AVX512 vectors is set in stone at compile time, the same instruction encoding is used for all widths of SVE. So how does that work then? Well, you're supposed to detect the length of SVE at runtime, then write your loop in a way such that it will work at any length of SVE. Of course, this also comes with some overhead, but it also comes with the advantage that you can write code once, and your code will scale all the way from a rinky-dink smartphone from today, up to a futuristic supercomputer with 2048-bit wide vectors. In theory anyways. Here's 3 generations of ARM CPUs available on Amazon Web Services. All 3 CPUs are capable of 428-bit Neon instructions. The Graviton 3 can do 2 256-bit SVE instructions per clock, which is the same peak throughput as 4 128-bit instructions per clock, but should be a little bit more performant and power efficient by doing more per instruction. But then you might be surprised to learn that the next 2 generations, the Graviton 4 and 5, can only do 4 128-bit SVE instructions per clock. And this tracks with the overwhelming majority of ARM machines that feature SVE. When it comes to consumer ARM devices that support SVE, every single one of them only supports 128-bit SVE. And so, the extra code that you need in your loop to support vector length agnostic loops might actually make SVE code slower than the equivalent Neon code. Crap. Let's take things even further by stealing some SVE code from later in the video. We save one instruction here by using the SVE code. But hey, I'm emulating the 128-bit vectors of the PlayStation 3. How will this work if we execute this on something like the Graviton 3? Well, similar to how AVX instructions work at lower width, the Neon instructions preceding and following our 256-bit SVE instruction will zero out the upper 128 bits of the 256-bit register, so actually, the code is still correct here. However, I've still chosen to only emit SVE instructions when the SVE length is detected as 128 bits. This is because it's not obvious that the SVE instructions will be a speedup at wider lengths. Imagine some hypothetical CPU that can do 4 128-bit Neon instructions, but just one 512-bit SVE instruction. Even if we save 2 Neon instructions for each SVE instruction we execute, we'll still end up slowing our code down. Since everything that supports SVE on consumer hardware is currently 128-bit only, we'll just check for 128-bit SVE support, and review it on a case-by-case basis in the future when a more capable consumer hardware is released. You might think that I'm wrong for taking this approach, but if we look at this ARM press release, they mentioned that they got a 10% uplift in performance for decoding AV1 video, which is probably the same video codec that you're using to watch this very video. Since the AV1 decoder in question, David, is open source, we can see exactly what code this blog post is referring to. Just like with RPCS3, they designed the SVE code to interleave together with Neon code, effectively dropping the benefit of scalable vector lengths. But why? Let's dive into this piece of code. Here, they're interleaving Neon and SVE instructions together, just like with RPCS3. We can determine that the instructions are using SVE by how the registers are addressed. The SVE instructions refer to the registers by Z. The Neon instructions refer to the registers by V. The Z and V registers are aliased, so Z3 and V3 reference the same register. Now, why are they mixing SVE instructions and neon instructions? Remember, we used S. earlier in the video, and that was a neon instruction. They're also using the neon encoding of TBL, even though there also exists an SVE encoding of TBL. Well, the neon version of S. only works on bytes. The SVE version of S. can optionally work with half-words, 16-bit values. Since these registers are denoted with .h, we know it's the half-word version. TBL is another story. These are the shuffle indices used by these TBL instructions. Since these TBL instructions are encoded to take two inputs, values between 0 to 15 will take values from the first input, and values between 16 to 31 will take values from the second input. If this TBL were SVE encoded, and we executed this instruction on a machine with SVE width of 256 bits, then values between 0 to 31 would take from the first input, and values between 32 to 63 would take from the second input, which would break the intent of the code. That's a bit of a problem when using TBL and SVE. The behavior isn't really agnostic to vector length, which, because TBL works this way, it's not really possible to use TBL in an SVE loop unless you specialize it for every vector length permutation. Which is absolutely awful. Poop. SVE 2.1 adds TBLQ, along with a lot of other instructions. What TBLQ does is restrict the shuffles to working within 128-bit lanes, not unlike how the 256-bit and 512-bit versions of SHUFB work on x86. Essentially, each 128 bits of a vector acts as its own 128-bit TBL, without being able to index past any 128-bit barrier. Of course, every current ARM CPU today that supports TBLQ only supports 128-bit SVE, so ironically, these three TBL instructions, Neon TBL, TBL with SVE, and TBLQ, all behave identically on every single SVE 2.1 machine. Anyways, point is, by using Neon TBL, they ensure that this code will still work correctly on 128, 256, and 512-bit SVE or larger, while being able to take advantage of new instructions that can accelerate their problem, like the S. that works on half-words. If interleaving Neon and SVE, and ignoring the entire scalable aspect of SVE is a viable approach for ARM employees to commit and write blog posts about, then it's good enough for RPCS3. Anyways, after consuming all this cursed knowledge on SVE, I was finally ready to sit down and start accelerating a few parts of RPCS3 with SVE. But there's one problem. My Odin 2 doesn't seem to report SVE as being present? Okay, hold on, did I misread some specs when I bought this thing? Okay, let's double check it. The A510 support SVE, the A710 support SVE, the A715 support SVE, and the X3 supports SVE. What's going on here? Turns out, Qualcomm disables SVE support in the hypervisor. Why? I have no idea. I really have no idea. The whole reason I bought the Odin 2 over the Odin 3 was because the Odin 2 had a CPU that supported SVE, but I guess whatever, man. Fuck it, dude, none of this matters. Fuck you. So anyways, I wrote my SVE code against QEMU, because nothing can ever be simple. I'm literally running an emulator in an emulator. Emulatorception. There's three SVE optimizations we added to the emulator. First, for the FMS instruction, when emulated with Neon, we need to negate this value because there's no equivalent multiply-subtract instruction, so negating the add-in when using FMLA is equivalent. With SVE, we have FNMLS, which, wouldn't you know it, is equivalent to FMLA with the add-in negated. I'm not really sure why they write it like this. Whatever. We save on one negate instruction, but since the instruction takes a predicate, we need to use this ptrue instruction to fill a predicate register with all ones. The good news is that LLVM should be able to recognize this pattern and only materialize the ptrue predicate once, for many usages of FNMLS. By the way, I think AVX512 has a more elegant solution to this problem. When encoding an AVX512 instruction that takes the mask register as input, encoding the mask register of 0 will cause the instruction to not read any mask register, and execute as if all mask lanes are true. Remember how we optimized the SBU multiplies with the Neon widening instructions? The SVE widening multiplies are even closer to the behavior of the SBU multiplies, because moving data to one side of a register doesn't really make much sense when supporting vectors of varying length. MPY-HHU, MPY-HHA, MPY-HHAU, MPY, MPY-HH, MPYU, MPYUI, and MPYA all turn into just one instruction with SVE, and MPYS turns into just two instructions. That's some pretty damn major savings. Finally, we have an optimization for rotate instructions. Not like RODM, which is a shift instruction in disguise, but for proper, vectorized rotate instructions. When the rotate is constant, we only need two instructions to emulate a rotate. Let's first look at how an x86 machine with AVX2 handles this. For instance, if we're rotating left by 8, we shift left first by 8. Then we can shift right by 32 minus the value we shifted left by, so we can shift right by 24. Finally, we OR these two values together, giving us our result. On ARM, this process is simplified because we have URSA, which shifts right and adds. allowing us to skip the OR operation. Unfortunately, URSA only takes constant values for shifts. In the SHA-3 Neon extension, we have a real rotate instruction in XR. Sort of. XR also XORs two values together before rotating by a constant value. However, it only allows you to rotate 64-bit values, which isn't useful for any of the SBU rotates. With the SVE2 encoding of XR, you can rotate bytes, half-words, and words as well, which finally gives us a single instruction rotated solution for all of these instructions, provided the rotate values are constant. Of course, XR also has that XOR operation, so we need to zero a register, but hopefully we can materialize that constant earlier. By the way, if you have AVX512, you can just get rotate instructions, both immediate and variable. Alright, maybe I'm talking about AVX512 too much. Have you ever been lied to before? Did anyone ever tell you ARM was a simple instruction set, where each instruction does a single operation? They were lying. Now that you know the truth, you should make it your new purpose in life to correct people on the internet. Just like me. Because consumer machines with SVE are so rare, I tested the functionality of these optimizations in QEMU. I'm literally emulating an emulator. But I wanted to know how much faster the optimized code was. Fortunately, the latest Snapdragon laptops support SVE. Unfortunately, they're a little bit outside my price range. Just a little bit. But, thankfully, the fine folks at Best Buy let me run RPCS3 directly on one of the demo units. By the way, these charging cables are supposed to set off an alarm if you remove them, but this demo unit somehow isn't set up correctly. The Best Buy employees were mortified. Look here though, by running synthetic benchmarks on the Best Buy laptop, we were able to observe a 10% performance uplift in a simple loop that uses a lot of multiply instructions. Remember that there are also a lot of load store instructions, as well as loop bookkeeping, so that's pretty nice. However, outside of these synthetic results, I think the gain from enabling SVE will be pretty slight, unlike with AVX512. Still, a win is a win. If you let me relate SVE to AVX512 one last time, it's regarding the rollout for SVE. It's a mess, just like how it's been for AVX512. See, all these CPUs have AVX512, but these CPUs have AVX512 disabled despite it being present on the core, since the recently introduced little cores don't have AVX512. The very next generation of Intel CPUs will support AVX512 across the board, but man, what the hell have they been doing? The rollout for SVE has been similarly confused. It's present on chips from Google, from Samsung, and from MediaTek, but the two companies responsible for the highest performing ARM chips, Apple and Qualcomm, it's been missing. The latest chips from Qualcomm finally do support SVE, but they've been inexplicably disabling it on chips that do fully support SVE, like the Snapdragon 8 Gen 2. With Apple, it's a little bit more excusable, as their cores weren't designed to support SVE, but it's still disappointing to see it missing. Actually, you might have heard that Apple supports SVE, but what they support is SSVE, Streaming SVE. To execute Streaming SVE, we need to enter Streaming mode, which wipes all of the neon registers upon entering Streaming mode. Similarly, exiting Streaming mode also wipes all registers again. Remember that our SVE usage looks something like a big pile of neon instructions, 1 or 2 SVE instructions, and then we immediately return to executing neon instructions. And so for our use case, Streaming SVE instructions are absolutely worthless. Subscribe to What Cookie? What does that mean? I sponsored the video myself this time, so I'd appreciate if you could subscribe if you made it this far into the video. I purchased a lot of equipment out of pocket to make this possible, so sharing the video with others who would enjoy it would help me out a lot. You can also hit the join button if you'd like to support me. This will help me justify spending more time working on the emulator and making these videos for you guys. That being said, my videos will always remain free for all and every view is appreciated. Thank you! You know, people talk about bottlenecks a lot when it comes to performance. Thing is, you can't always bottle up everything in such a clean analogy. If I'm optimizing for my desktop, then yeah, bottlenecks become clear. We have 8 fast cores, a power limit approaching 100 watts, water cooling, the GPU has its own memory, its own power limit. When we're emulating a PlayStation 3 game, where will the bottleneck lie? 95% of the time, it's going to be in emulating the SPUs. But on the Odin 2, where's the bottleneck? The GPU and CPU share memory. They sit on the same die, and heat from one will heat the other. They have a shared and meager power limit, and only 5 of the cores are fast. 3 of the threads must be relegated to the A510s, which are of questionable value. Point is, even if we appear to be SPU limited on the Odin, optimizing other code might free up power limits, might reduce pressure on shared resources like memory and cache, or might reduce overheating. To that end, I had one last optimization up my sleeve, an optimization that I didn't bother completing because it wouldn't impact the bottleneck on my desktop. But on the Odin, it might help. Earlier, I made this video which covered the use of user mode wait instructions on Intel and AMD. In that case, we were only using them to wait on a timer, but those instructions are also capable of waiting on a cache line, entering a low power state until another thread modifies the cache line. Fortunately, ARM has equivalent instructions that allow us to wait on a cache line, LDAXR together with WFE. Typically, Intel and AMD implement the same instructions, but this is a rare case where Intel and AMD appear to refuse to implement the same instructions, despite having nearly the same behavior. For our purposes, they work identically, but have a slightly different interface. WFE is a little more alien, but it's still close enough to be used together. I implemented functions that hide the complexity of these disparate interfaces and hooked them up to some spin locks in our GPU emulation code. The result? Savings of 4 watts on my desktop in a scene at a locked frame rate. From 42 watts down to 38 watts. Not bad, considering the machine idles at 30 watts. With the frame rate unlocked, we saved 1 watt, from 49 watts down to 48 watts. On the Odin, we had savings of 1 watt in a simple scene, from 6 watts down to 5 watts. On a tougher scene, we dropped half a watt, from 10 watts down to 9.5 watts. There's a lot of optimizations that almost work, but are just slightly incorrect so we can't use them. This is one near-miss optimization that bothers me. So, first, you should know that we need to clamp SPU floating point numbers, because the SPUs interpret values of nan and infinity as normalized floating point numbers. This is typically done by combining an unsigned min instruction with the largest negative floating point value representable on ARM and x86, and a signed min instruction against the largest positive floating point value representable. The PlayStation 2 shares the same floating point behavior, so PlayStation 2 emulators also take the same solution. This is needed because values like nan propagate. Any floating point operation with nan results in nan, so games will break without handling them. On x86 with AVX512, we can turn this into a single instruction because the instruction vRange_PS can do both the positive and negative clamping at the same time, but also has some incredibly specific behavior around nan that is advantageous to us. On the latest ARM chips, there are new clamping instructions, floating point clamp instructions, as well as signed and unsigned clamping instructions. Unfortunately, the behavior of fclamp around nans isn't what we want, and the integer clamping instructions aren't quite what we need either. We're almost at a one instruction solution here, but none of the instructions are quite exactly what we're asking for. This is Cellmark, a benchmark created by SageMono. This benchmark is intended to be used with an overclocked PlayStation 3 to test how much faster an overclock is versus a baseline PlayStation 3. But we can also just run it in the emulator. This is how fast the benchmark runs on my desktop. It's about twice as fast as the real PlayStation 3. Here are the results on the Odin 2. You can see the 4 different speeds on the cores. The X3 Prime core does pretty well, the 2 A715s are alright I guess, as are the A710s, and the A510 is just not very fast at all. Remember, the X3 core runs at 3.2 GHz, and the A715s and A710s run at 2.8 GHz, and the A510s run at a piddly 2 GHz, while the PlayStation 3's SPUs run at 3.2 GHz. So, while we only reach 78% the speed of a real PlayStation 3 here, we are running at a clock speed deficit relative to the original system we're emulating. Alright, it's time for the lightning round. Here are the last fixes and optimizations. Remember how we used TBL to emulate SHUFB properly? We also needed to use it in some other places. We don't actually save any instructions directly here, but we do simplify the number of constants we need loaded in SBU LVM. One optimization made earlier for x86 was to inline timer reads directly into the recompiled code. It's a one-line change to enable that for ARM as well. In our PowerPC code, we have some extra code to work around x86 fmax and fmin behavior. The ARM fmax fmin behavior just matches PowerPC, so we can optimize simply by putting that code behind an ifdef. Here's a stupid one. We need to check that FMA instructions are present on x86, because it isn't baseline in 64-bit x86. For ARM it is baseline, but to remedy this we were checking if the CPU name had Cortex in it. That means that any Apple or Qualcomm CPU is missing out on FMA instructions. The PlayStation 3 is the FMA machine. Here's how much slower Cellmark is without FMA enabled. Similarly, we are using the LLVM CPU name to enable disable features, but thanks to nonsense like the Snapdragon 8 Gen 2 missing SVE, despite all the cores supporting SVE, LLVM incorrectly assumes that the machine can execute SVE instructions. Fixing this resolves some crashes on illegal instructions, and enables LLVM to choose the best instructions possible. The Odin 2 is a relatively anemic device. I like to think of it as half a Steam Deck. It has a memory bus half the width of the Steam Deck. It draws around half the power that a Steam Deck does, but it features a more advanced and power-efficient manufacturing process from TSMC, and the memory does run at a much faster speed, despite being half the width. After all these optimizations, the Odin 2 is approaching Steam Deck performance with half the power. In fact, we've optimized the CPU side so much that the bottleneck has shifted in many games like Demon's Souls to the GPU. With just a few more hardware generations, I know that we can exceed Steam Deck performance with less than half the power. I've also got these other ARM-based handhelds that are more of a pocketable size. Today, they're nowhere near enough to run PlayStation 3 emulation, but I know that in time, our PS3 will be running on devices that fit in your pocket and cost under $100. You know, if AI demand doesn't price us out of consumer hardware forever. Beyond tiny devices, ARM is also expanding into larger devices. ARM laptops are becoming more common across Windows, Mac, and Linux devices. Even if I personally can't see myself justifying the purchase of one, there's no doubt that personal computers running on ARM are here to stay. I spent years studying the PlayStation 3 and x86 to eke out every performance increase possible. In just a few months, I was able to close most of the gap between x86 and ARM in our PS3. We fixed bugs in our code. We worked around bugs in LLVM, and we came up with a bunch of genuinely novel optimizations, granting us 60% performance at just 75% the power. Boy, I hope all those optimizations didn't crack my Odin too.
Thank you so much for playing my game.